All right, welcome to lecture 7.2 covering right triangle trigonometry. And the word trigonometry actually breaks down to the T-R-I-G-A-N, I believe, it stands for triangle in Greek, and metry is measurement. So trigonometry is all about using a triangle to gain insights into different measurements and functions that go along with that. So we'll go ahead and move forward. All right, so using right triangles to evaluate trigonometric functions. The first thing that we need to establish, welcome Jeremy, same thing as last lecture, just ask any questions if you have them. I've already let Karen know to do the same. All right, so what I have at the top of the page here is what is known as the unit circle. Now, we have an entire section coming up on the unit circle, and we'll get to know it in a very detailed and intimate way. But on the surface, what the unit circle actually is simply a circle of radius 1 with the center at the origin. So we use this circle as a basis to start establishing right triangle relationships. With having that radius as 1, you can see this inscribed triangle that I have here. Let me highlight it for you. So there's my radius, which is 1 by default, because I've said, okay, I've got a circle of radius 1. So all the way around, my radius is going to be 1 in that circle. If I drop a plumb line, if you will, down from that point on the circle, it's going to hit at a 90-degree angle to my x-axis here. So here's the right triangle that I can form no matter where I put the point on the circle. So let's say I put a point on the circle here. Okay, I know the hypotenuse of my right triangle is 1. I can move up to the x-axis there, and then I've got a right triangle that I can talk about with a leg length of x and a leg length of y. So looking a little further into that. So there's just some information given around the outside. So here we go. The side opposite of the angle corresponds to the y component of the point that you found on that circle. And then the side that is adjacent to your angle theta here is corresponding to the x component of that point on the circle. So that's a basic idea of what the unit circle is. Now, we're going to extract specifically 2 triangles in this particular lesson. 2 right triangles, a 30-60-90 and a 45-45-90 triangle, and take a closer look at the characteristics that start to bubble up from these right triangles. So just to clarify, you always have your angle theta, or that they're calling this angle T here. That's the angle whose vertex is situated at the origin if this thing is inscribed in that unit circle. You have the adjacent side. Adjacent just means next to. So this is the side or the leg of the right triangle that's next to the angle that you're using to work with this triangle. And then you have the side that is opposite that angle. And then, of course, your hypotenuse is always the side that is directly across from your right angle. So it is important that you know where the adjacent, opposite, and hypotenuse sides of the triangle sit. Okay, so now we're going to start moving into the trig functions. And the first three that we study, which, by the way, I need to point out that your textbook has a typo in it. Let me go ahead and show you that. The first three that we study are the sine, cosine, and the tangent. So notice when they come down here to help you understand the relationships of those sides, they actually typed secant there. So that is a typo. It is correct in your notes that I've given you, but it is incorrect in the text, and I've already sent in an error message to them to get that corrected. But I just wanted to point that out in the lecture video. Hopefully by the time many of you are watching this video, they will have that corrected, but I definitely wanted to point that out. So it's correct on your notes. I have tangent written there. Okay, so given a right triangle with an acute angle of T, so let me get a nice bright color that will stand out here. So here's angle T that we're talking about. The trigonometric functions are, okay, so we have sine, well, the first three trigonometric functions. We have sine, cosine, and tangent. You're used to seeing them written like this, S-I-N, C-O-S-T-A-N. Those are the buttons that show up on your calculator. So the sine of angle T, and this is just a relationship that is built in this right triangle. The sine of angle T is the value that you get when you divide the length of the opposite side, so that's opposite angle T, by the length of the hypotenuse of the triangle. So in this triangle right here, we would have our y value over 1. We know our hypotenuse is 1 because this is the unit circle we're working with, which is just y. So y over 1 is just y. Okay? The cosine is given by the ratio of the adjacent side of the triangle to the hypotenuse. So that's x over 1, which is just x. The tangent is given by the ratio of the opposite side over the adjacent side. So in this case, that is y over x. All right, so since the sine and the cosine are being divided by 1 and end up just giving you the y and the x lengths, you can see in this drawing over here, whenever you find the cosine, you're finding the length of that adjacent side. And when you're finding the sine, you're finding the length, and it's the sine of theta, by the way. You're finding the length of the vertical side or the opposite side. So the coordinates of that point that lie on the circle are cosine theta, sine theta. The tangent, that ratio of the opposite side over the adjacent side, actually gives you the length from the point on the circle. Remember, for a line to be tangent to something, it intersects it at one point. So if I continued that line, you'd have that, but it actually gives you the length from that point on the circle back down to the x-axis, or up, depending on where that point is on the circle. So that is actually a visual picture of, okay, what is sine, cosine, and tangent? Well, we know it's these ratios, these relationships between the sides of the right triangle. But and I think that the reason I included this picture, which this is not in your book, I went and found this picture. I liked that it showed what the tangent actually is, and even though you're gaining that value from the right triangle on the inside, it's corresponding to a length that is tangent to the circle on the outside. Okay, so there is a mnemonic device that is very common to use to remember these first three trig functions and how to find them. And that is SOHCAHTOA. So is sine is equal to opposite over hypotenuse. Ka is cosine is adjacent over hypotenuse, and TOA is tangent equals opposite over adjacent. And then I just included another picture here of what these first three trig functions represent. Are there any questions so far, or is this pretty straightforward for you? Screen check if you're good to go so far. Karen, are you okay? Okay, great. Okay, so what do we do with all this? Well, one thing we do with this is to find the actual trig functions using different sized right triangles. All we have to know are those ratio relationships that we just discussed. So we have this given right triangle here that, I think my pages have gotten out of order. Give me just a second. Okay, now I'm back in order. I have all my notes worked out here. Okay, so I will just remind you of SOHCAHTOA, just so we can have that to refer to. And we are asked to find the sine of t, the cosine of t, and the tangent of t. Notice angle t lives there. And the sine of t is given by that relationship of opposite over hypotenuse. Don't forget, actually I'll just label the whole triangle with their respective labels. Remember, across from your right angle is always your hypotenuse. The side that's touching or next to the angle that you're working from is adjacent, and the side that's across from the angle that you're working with is your opposite. So the sine of t is given by opposite over hypotenuse. That is just 7/25. That is the measurement of that function. Cosine of t is adjacent over hypotenuse, and my adjacent side is 24, my hypotenuse is 25, so 24/25, almost 1. And my tangent is opposite over adjacent. And until you get really keen with working with these triangles, you know, I suggest you write their relationship so you don't forget. And the more you write it, the more it's going into your brain so that at some point you'll just know it and you won't have to write it any longer. So opposite over adjacent. Y'all good to go? Jeremy says yes. Karen says no. Okay, Karen, what's your question? Oh, Karen says yes. Misfire there. Okay, the next three trig functions. We have secant, cosecant, and cotangent. We are given that the secant is actually the reciprocal of cosine. So 1 over the cosine of t is what the secant is equal to. Well, we know the cosine is equal to the adjacent over the hypotenuse. That's 1 divided by the adjacent over the hypotenuse. We know we never divide fractions. We multiply by the reciprocal, so this is 1 times the reciprocal hypotenuse over adjacent. So we get that the secant is the hypotenuse over the adjacent. And if we go back to this unit circle triangle with the x and the y and the 1 as the hypotenuse, we would get that that is 1 over x. Okay? The cosecant is the reciprocal function of the sine. So that's 1 over opposite over hypotenuse, which is 1 times hypotenuse over opposite, which is just the hypotenuse over the opposite, which is 1 over y. And finally, cotangent is reciprocal to the tangent. So that's 1 over, well, the tangent is opposite over adjacent. So that's 1 times adjacent over opposite, which just equals the adjacent over the opposite, which is x over y. And this box here that I included on your notes, this just reminds you of the relationships, the reciprocal relationships. So sine of t is reciprocal to cosecant, cosine is reciprocal to secant, tangent reciprocal to cotangent. Okay, so many problems that you're going to encounter ask for you to, they'll either say solve the triangle, or it'll ask for all 6 of the trigonometric functions. If it asks you to solve the triangle, it wants you to find all sides of the triangle and all angles of the triangle. If it asks for the 6 trig functions, you need to do sine, cosine, tangent, cosecant, secant, cotangent. And whenever I do this type of work, I like to set up my functions so that the reciprocals are opposite of each other, the reciprocal functions, just to keep reestablishing in my mind that relationship. So we're asked to find all 6 trig functions here. So what I'm going to do is I'm just going to set up, okay, I need to know the sine of t, and then I know that once I find the sine of t, all I have to do is flip-flop it to get the cosecant of t. So I'll always set those up across from each other. And then I have the cosine of t, which is reciprocal to the secant of t, and then the tangent of t is reciprocal to the cotangent of t. So I always set my 6 trig functions up like this. Okay, and I'll usually write this at the top of my page too, just as an extra reminder. Okay, so here's my angle t, which means 33 is opposite, 56 is adjacent, and 65 is the hypotenuse. Okay, the sine is the opposite over the hypotenuse. So the sine in this case is 33 over 65. So since I already know that cosecant is the reciprocal function of the sine, I can go ahead and say, well, that means that cosecant of t has to be 65 over 33. Cosine is adjacent, 56, over the hypotenuse, 65. Secant is reciprocal to cosine, so 65 over 56. And the tangent is the opposite over the adjacent, and cotangent is reciprocal to tangent, so 56 over 33. Any questions about finding those 6 trig functions? Green check if you're good with that. Okay. Jeremy, I don't think you were in the room when I told Karen this, but you'll be pleased to know we'll probably be done early with this lesson. And I think that's a welcome sound to you after the hour-and-a-half lecture over 7.1. There was just so much to cover in 7.1. All right, so now we're going to start drilling down into these special triangle relationships that we have set up with the unit circle. And that is a 30-60-90 triangle, right triangle, and a 45-45-90 right triangle. These are the backbone of what we'll be doing for the rest of the semester, really. So it's very important that you understand how to work with these triangles. And really this information that you're about to get, it would be quite beneficial for you to just put it to memory. Okay, so consider that both of these sketches are sketches of the unit circle, which is going to make the hypotenuse of both of these right triangles 1. Now, we know that if we have a hypotenuse of 1 here, and we force this to be a 60-degree angle, that and if we drop our plumb line down from that point on the circle, creating the right angle, this is half of an equilateral triangle. So it is absolutely necessary, since this is half of an equilateral triangle, we know if we finished off this triangle over here, an equilateral triangle, all angles are equal, which means it's a 60-60-60 triangle. And all sides are equal. So this side is equal to 1, and this entire side over here is equal to 1, which is how I am able to say that that side that is adjacent to the 60-degree angle there is equal to 1/2. From there, I use my Pythagorean theorem, which we know that comes from right triangles, or used with right triangles. I can use my Pythagorean theorem to figure out that the length of the opposite side of the triangle is, which is the height of my triangle, since I've dropped it down from the vertex perpendicularly to the opposite side, is equal to the square root of 3/4. Now, we're not going to leave this as the square root of 3/4. We have to simplify this. This simplifies to the square root of 3 over the square root of 4. So that is the square root of 3/2. So if I pull out that 30, 60, 90 triangle, so this is 60, which for the record corresponds to pi/3 in radians. That's a 3. That's terrible. There's my 90-degree angle. And 90 degrees is pi/2. This is my 30-degree angle, which is pi/6. Okay, so if I pull that triangle out, I have 1/2. This is the ratio that my sides always fall into. Square root of 3/2 and 1. Now, these are multipliers for those sides. So whatever my hypotenuse is, it's 1 times whatever that length. So this is so that you can apply it to any 30, 60, 90 triangle. You may not see that side written as 1 unless it's the unit circle we're talking about. So it's always in that ratio of 1 times whatever that side is, and 1/2 times whatever this side is, square root 3/2 times some S side. So those S's are all the same value, and they multiply with each of the respective unit circle measurements given for that side. I feel like I rambled on that. Did that make sense? So we're setting up a relationship here for any 30, 60, 90 triangle of hypotenuse any length. Is that okay? Did that gel with y'all? Okay, Karen says yes. Okay, Jeremy says no. Jeremy, before I try to ramble more about this, I think this will become much clearer when we do the example on the next page. So for right now, just say, okay, great. Let me ask you this. Do you understand where the 1, the 1/2, and the square root of 3/2 come from? That's the important part right now. Okay, as long as you understand that, you're okay. The S's that I just wrote in there will make sense in just a moment. Okay, so we have now the 45, 45, 90 triangle, and these set up ratios of 1 again, so that's 1 times S. Actually, I'll take that off of there and wait to pull the triangle out, because I need to simplify the square root of 1/2, because you're never going to see it written that way. You're going to see it in its simplified form. So this is the same thing as the square root of 1 over the square root of 2, which is 1 over the square root of 2. We know we can't leave a root in the denominator, so we need to rationalize the denominator. And I do so by multiplying by that clever form of 1, square root of 2 over square root of 2. The square root of 2 over square root of 2 times 1 over square root of 2. 1 times the square root of 2 is just the square root of 2 in the numerator. The square root of 2 times the square root of 2 is the square root of 2 squared. Whenever I square a square root, those are inverse operations and undo each other, so I end up with square root of 2 over 2. So these two sides are given in the ratio of square root 2 over 2 for my two legs, both my opposite and my adjacent sides. And the hypotenuse is 1. So if I pull that triangle out, so this is a 45, which is pi over 4. And this is 45 as well, which is pi over 4. I'm in the unit circle, so my hypotenuse is 1. And then I have square root 2 over 2 for this side, square root 2 over 2 for this side. Now, if I want to expand that to any 45, 45, 90 triangle, I'm going to be multiplying by a common factor of s with all of those sides. And I'm about to show you what that looks like. Oh, let me grab these two triangles and put them on the other page for us to look at. Okay, so there's one of them. Let me go back and grab the 45, 45, 90. Okay, so this question here, or example here, says, give the exact values of the trigonometric functions of pi over 4 using the side lengths. So we have pi over 4 and we know that that corresponds to our 45, 45, 90 triangle, pi over 4. And this is pi over 2, the 90-degree angle. Okay, because we know that we've already established the side lengths of this triangle, and actually this isn't the one that gives us insight to the S yet, but the next problem does. It'll clarify the S's that I have written there. So we have the 45, 45, 90 triangle. These are in proportion to each other. 1 square root 2 over 2 for this side, square root 2 over 2 for this side. I'm just going to label my opposite, adjacent, and hypotenuse. So we'll consider this the angle. We could choose either of them to work from since they're both pi over 4. We'll choose that one, which means this side is adjacent, this side is opposite, and this is the hypotenuse. And actually, yeah, I'm going to go ahead and include the S's on this. So these are in proportion There we go. Okay, so I also want to give myself something to remind me of the trig functions, and then set up my space to calculate the 6 trig functions. So I have the sine of pi over 4 equals, and that is reciprocal to the cosecant of pi over 4. And then I have the cosine of pi over 4 reciprocal to the secant of pi over 4. And then finally the tangent of pi over 4 reciprocal to the cotangent of pi over 4. Okay, so sine is opposite over hypotenuse. So here, my opposite side is square root 2 over 2 times s. And I'm dividing that by the hypotenuse, which is 1s. So that's just s. Here, because those s's are just multipliers to move you into different sized triangles that are still 45, 45, 90, notice these divide out because I'm working with just a general unit circle-based triangle here. So that leaves me with the square root of 2 over 2. Now, I automatically know that my cosecant, because it is reciprocal to my sine function, is 2 over the square root of 2. However, you cannot leave that square root in the denominator, so I need to rationalize the denominator by multiplying by 1 in the form of square root 2 over square root 2. That is 2 square root 2 over, well, that's the square root of 2 squared in the denominator, so that's just 2. My 2's divide out, and I'm just left with the square root of 2 for the cosecant. All right, the cosine is the adjacent square root 2 over 2 times s over the hypotenuse, 1 times s, which is just s. Once again, I divide out those s's because those are just multipliers creating bigger triangles that are still 45, 45, 90. And I'm left with square root 2 over 2. The secant is the reciprocal function, and I've already done the work for it. This is just square root 2. And finally, the tangent is the opposite, square root 2 over 2s, over the adjacent, square root 2 over 2s. Everything divides out, and I'm left with 1. The reciprocal of 1 is 1. Green check if you're good so far. Red X if you've got questions. Yay, Jeremy, I'm glad to see that. Karen, are you okay? Great. Okay, so this is an interesting relationship that falls with a 30, 60, 90 triangle. And so I wanted you to find this relationship. So I'm asking you to find the sine of and the cosine of both pi over 3 and pi over 6. Okay, so we'll start with the sine of pi over 3, and then we'll find the cosine of pi over 3, and then we'll find the cosine of pi over 6, and the sine of pi over 6. And I have them set up like this for a reason. Okay, so the sine of pi over 3, sine the sine, okay, so pi over 3 is this angle right here. That's that 60-degree angle. The sine of pi over 3 is the opposite, which is square root 3s over the hypotenuse 2s. My s's divide out, and I get square root 3 over 2. The cosine of pi over 3 is the adjacent, which is s, over the hypotenuse, which is 2s. My s's divide out, and I'm left with 1/2. Okay, now let's go back and get the pi over 6 functions. Let me get a different color here. So pi over 6 is that 30-degree angle there. The cosine of pi over 6 is adjacent, so adjacent to that is square root 3s over the hypotenuse 2s. My s's divide out, square root 3 over 2. And the sine is the opposite, which is s, over the hypotenuse 2s. My s's divide out, and I get 1/2. Here's what I wanted you to see. When you are dealing with right triangles, the sine of one of the angles is going to be equal to the cosine of the other angle that's not the right angle. And the same here. The cosine of the angle is going to be the same as the sine of the opposite angle there. That's pretty interesting, isn't it? In my nerdy world, things like this are interesting at least. So what this is, Karen's typing probably about my nerdy world. Yeah. I think it's interesting. Okay, so these relationships are known as co-function complements. Co meaning with, so these functions work together to complement each other. Complements kind of complete the, they complete each other, they complement each other. So this is all of those relationships that fall in that manner. So cosine of t is equal to the sine of pi over 2, which is your 90-degree angle, minus that first angle that you are working with, t. That's going to give you the other part of the 90 degrees that were left on the inside of the triangle. So sine and cosine go together in this manner, tangent and cotangent, secant and cosecant. All right, let's try one down at the bottom here. We have the cosecant of pi over 6, and we're told that that equals 2. And we say, okay, well, what is the secant of pi over 3? Well, if we knew that cosecant and secant were set up in this relationship, we said, well, that equals 2. But we can find it or show that to be true by saying, okay, well, if the cosecant of pi over 6 is equal to 2, I'm told by this relationship that that should be equal to the secant of pi over 2 minus my t values, that's pi over 6. Okay, so continuing, that is the secant. Okay, I cannot subtract these fractions without having a common denominator. So to get that common denominator, I'm going to multiply that first term by my clever form of 1, which is 3 over 3, to get that denominator to 6 so that I can combine those terms. And that gives me the secant of 3 pi over 6 minus pi over 6. So that is equal to the secant of 2 pi over 6, which is the same thing as the secant of pi over 3. Okay, now I know. Okay, they ask for the secant of pi over 3. I now know that the secant of pi over 3 is equal to the secant of pi over 2 minus pi over 6, which sets up my relationship to be able to say, okay, the secant of pi over 3 then also has to equal 2, just like the cosecant of pi over 6. Because pi over 6 plus pi over 3 is equal to pi over 2, which is at 90 degrees. So that's talking, this is setting up the relationship between a 30, 60, 90 triangle. Everybody good? All right. Okay. Now we are finally to the point where those S's are going to make sense to you, Jeremy. And actually, I'm going to go grab the 30, 60, 90 triangle again, way back here. Hopefully, this will be clear as mud after this one. Okay, let me paste that triangle here for us to look at. Okay. All right, so this question says we have a right triangle that has a pi over 3 angle in it. So once again, we're talking about the 30, 60, 90 triangle. So I'm just going to draw this triangle we're talking about. If you don't have a triangle drawn for you, you always want to draw it to keep yourself straight. So this is my pi over 3 angle. And then I have my pi over 6 angle. That's my 30 degree angle there. And then I have my 90 degree, which is pi over 2. I have a hypotenuse of 20. Okay, so according to what we found with the relationship of the sides of these triangles, and these relationships were gotten from the Pythagorean theorem. I didn't show that to you just for the sake of time with the lecture, but I'm sure that y'all are very, very much familiar with the Pythagorean theorem that says one leg of the right triangle squared plus the other leg of the right triangle squared is equal to the hypotenuse squared. That's how these side lengths were set up. Okay, so we know that this 20 is equal to 1 times S. So we have to use this information to figure out the other sides, and we already have the other angles of the triangle because we know that pi over 3 goes with pi over 6 with the 30, 60, 90 triangle. Okay, so the adjacent side is 1/2 S, and the opposite side is governed by the relationship square root of 3 over 2 times S. We have to figure out what S is. So we take the relationship that we already know about S. So at the bottom here I have 1S is equal to 20. If I divide both sides by 1, I have S is equal to 20. So now I can come and say, okay, well, if this is true, my adjacent side has to be equal to 1/2 times 20, which gives me a side length of 10. And the opposite side has to be consistent with the relationship of square root of 3 over 2 times my S, which is 20 square root 3 over 2, and then I can come back in and say 2 goes into 2 once and 2 goes into 20 10 times, and that leaves me with 10 square root 3. And the only other thing we were missing was that other angle, and we've already found it. The other missing angle was pi over 6. Did that help you understand that, Jeremy? Okay, good. I figured it would. Karen, are you good? Okay, great. Last page. Okay, so we can use right triangle trigonometry to solve applied problems. So it's important that you know these two very specific definitions. The angle of elevation of an object above an observer relative to the observer is the angle between the horizontal and the line from the observer's eye to the object. Line is used very loosely there with me trying to draw it. Use your imagination on that. And the angle of depression is starts at the object, the height of the object. Oops, got my keypad there. The height of the object and that angle down to the observer's eye. So you've got these two angles, angle of elevation and angle of depression. Okay, so if you look down at our problem here, let's see, we need the side of a house here. Y'all get to see my lovely ability to draw. And here's my house. And let's say I have a window on the side of the house there. That's terrible. And I have this ladder that's going up to that windowsill. There's the ground. This is a ladder. Not a ladder that I would want to crawl up, but it's a ladder nonetheless. use your imagination. Okay, and what we're told is that this ladder needs to go up to the windowsill that's 50 feet above ground. So what we've just been told is that this leg of our right triangle is 50 feet. And it rests against the building, making an angle, and they really should have said an angle of elevation of 5 pi over 12. So this angle down here is 5 pi over 12. And they want to know how tall or how long is the ladder. So if we consider that angle of elevation our starting point, we have a value for the opposite side. And we're trying to figure out how long is the hypotenuse. The relationship that we know that relates the opposite in the hypotenuse is sine. So I start out with the sine of t being the opposite over the hypotenuse, and specifically with my problem here, the sine of 5 pi over 12 is equal to 50 over the hypotenuse, and I'm just going to use h for the hypotenuse. I'm trying to figure out the length of my hypotenuse, so I need to solve this equation for h. So to do that, I multiply both sides by h, and now I have h times the sine of 5 pi over 12 equals 50. And now I need to divide both sides by sine of 5 pi over 12. So what I end up getting is that these divide out there. I get h is equal to 50 divided by the sine of 5 pi over 12. Now, this is where you have to put it into your calculator. You have a sine key on your calculator. However, notice, this angle has been given to you in radians. So you have to make sure that your calculator is in radian mode to get a correct calculation. So to check that, at the very top of your calculator buttons, you have the mode button. Click that, and the third option down is either radian or degree. Make sure radian is highlighted. If degree is highlighted, just arrow down and put your cursor over radian and hit enter, and it'll change you to radian mode. And then you're ready to put this into your calculator, and I'm going to write exactly what I put into my calculator to get the correct answer. I did 50 divided by, I hit my sine key, and it opens up a set of parentheses. I did 5. I used my pi key. Do not use 3.14. You want to use pi, which is the second function on your caret key, which is all the way over onto the right-hand side of your calculator. And you divide that by 12 and then close that parenthesis. And when you put that into your calculator, you get that that's equal to 51.763800902. Jeremy and Karen, were y'all able to get that value in your calculator? Jeremy says yes. Karen says yes. Very good. So it tells us to round to the nearest foot. So the ladder is approximately 52 feet long. That's all I got for you today. I'm sorry I was not early finishing, but I think this was good information, and I hope this was helpful for y'all. If y'all don't have any questions, we'll call it a day. You're welcome, Karen. Thanks for coming.